of all, I just posted the practice test online. So on Canvas, if you go to Canvas and go to announcements, you'll see I made an announcement that says solution keys. And I posted solutions to basically everything that we've done so far. So solutions to the notes. Sorry, I didn't pull it up yet. Solutions to the in-class notes, solutions to the practice test, as well as the blank practice test so that you can download that and do that some more. Okay, let's start with our first question here. What is the basic factoring technique? What do we do to solve this problem right here? What question do you ask? Chelsea, get us started?
So it's what two numbers multiply to make the last term and add to make the middle term.
Yeah, exactly right. So what do you multiply to make 12, that you add to make 8, and you have to think about it for a second and say, well, here's my factor table of all the numbers that multiply to make 12, and 2 and 6 add to 8, and so you just report your answer, x plus 2, x plus 6. How do you know this is correct?
You foil.
You can just FOIL it out. Right? So you never have to sit there wondering, oh gosh, did I get the right answer? You can just FOIL it out and see if it works. Okay, what must you do before you can do basic factoring, like in a problem like this? Factor out numbers if you can. Factor out numbers if you can, so I can factor 3 out of all of those, and factor out a leading negative if there is one. So anytime there's a negative on the first term, you have to factor it out. So if I take out a 3 and I take out the negative, I divide each of those by 3, so that's just 1x squared, that's 8x, and that's 12. What happens to all the signs when you factor out a leading negative? Yeah, they all change. Plus becomes minus, minus becomes plus. So they just change. So I'm left with just this. And this, of course, is the same as that problem, so I would say that my completely factored expression is negative 3, x plus 2, x plus 6. And that's it. We would say that's factored. This is not set equal to 0, so you're done. You know, if it just said factor the expression, I factored it. If it was set equal to 0, then you'd have an extra step of saying, well, if something times something equals 0, then one of these is equal to 0. Now, one of those has to be 0. Obviously, negative 3 can never equal 0, so that's just silly. But x plus 2 could equal 0, and x plus 6 could equal 0, which means once you finish solving those, x is negative 2, x is negative 6. Negative 2 and negative 6 are the two numbers that I can plug into this thing, and it would be equal to 0. So that's the whole process. Why we factor is to convert an addition problem into a multiplication problem, so you can use the zero product rule so you can solve for x, which gives you the x-intercepts and knowledge about the original equation. Okay, how does factoring by grouping work? What do I do there? Someone who hasn't said something? Jessica? Yeah, put it in parentheses, and then what do? Yeah, factor the first one, that's x minus 4. I'll take out an x. What can I take out of the next one? Yeah, 8. So then I have 8 out of x minus 4. And what's really important right now? There's? Yeah, they have to be the same. So x minus 4, x minus 4. The fact that they're the same means that we can proceed with the factoring. So x minus 4 becomes one of our factors. And then the leftover bits out front becomes the other factor. And again, is this correct? We hope so. You'll find out as soon as you FOIL it back together and see if it actually works. So if I FOIL that now, first x squared, outer plus 8x, inner minus 4x, and then last minus 32, and I combine like terms, that's x squared plus 4x minus 32. Is that the same as the original? Well, in my original, the negative 4x and the 8x could have combined like terms. So yeah, negative 4 plus 8 is 4. So x squared plus 4 minus 32, x squared plus 4 minus 30 is the same. Okay, what is the difference of squares approach? How about, remind me your name again? Joseph. Joseph, tell me about it. What do I do here? Yeah, exactly right. So first you notice that 36 is a square number. So you say, well, that's really x squared minus 6 squared. And only because it's the difference, that is subtraction of two squares, you can rewrite it as the product of conjugates where it's x plus 6, x minus 6. Notice that you can even use this technique if 36 is not a square number. Now that we've talked about square roots, we could use this technique and just say, what if x squared minus 35? Right? 35 is just a little off from a number that's actually a square number, but I could still rewrite it as x squared minus root 35 squared. Right? That might look a little weird, but you can do it, right? Because what happens when I square the square root? It cancels, and it's just 35, and that is the problem. So I could write this as x plus root 35 and x minus root 35. So the fact is, x squared minus anything. You can do this technique of factoring it, but that's not very helpful to factor in the square roots. For the most part, we don't do that. The key is that it has to be minus. So what if I had said x squared plus 36? Can you factor that? No. That one just doesn't factor. Okay, so then our last one, if the first term is not 1x squared, what is the clever trick you must do? So this last example, I call this the long factoring method because it's a little longer. What do we ultimately have to do to this in order to factor it? Well, if setting it equal to 0 is something we can do if we actually want to solve for x and find the x-intercepts. We can factor this without setting it equal to 0. In fact, setting it equal to 0 is something you do after you're all done factoring. Then you're ready to set it equal to 0 and do the zero product rule. But first we have to factor. Yeah, we're going to multiply the first times the last term. So 2 times negative 30 is negative 60. And again, you do your factor table for 60. So 1 and 60, 2 and 30, 3 and 20, 4 and 15, 5 and 12, 6 and 10. Until you're all done, and then you're looking for which of those numbers add up to 7. Well, in this case, we're multiplying to make a negative 30, so it has to be a plus and a minus number. So which one has a difference of 7, 5, and 12, and we want the 12 to be positive and the 5 to be negative? Now, Jag, you're absolutely right. This is the procedure. You do the 2 times the 30, but what are we trying to do? And we're trying to rewrite that middle term. I like you, Josh said, split that up. That's true. You're trying to split up the middle term into 2 different parts so that you can do factoring by grouping. So by splitting the 7x into minus 5x plus 12x, first of all, we would all have to agree that this is valid, that I am simply allowed to rewrite 7x as negative 5x plus 12x because negative 5 plus 12 is 7. So this was a perfectly legit move. And now we're able to factor by grouping. So I can take out my x here, 2x minus 5. I can take out a 6 here, that's 2x minus 5. And since those are the same factors, the parentheses, now I know 2x minus 5 is one of my parentheses, and x plus 6 is my other parentheses. It's factored. So all of these factoring techniques are going to haunt you for the rest of your life. I mean, you're going to use them for the rest of your life. Right? These are factoring techniques that come up again and again. They come up in 150. They come up in a calculus class. They'll come up. So it's good to have these all, make a reference sheet and keep it handy. Hang it up in your house somewhere. That way you can always see how these techniques work. Finally, last question, how do you simplify a root? Let's say that I gave you the root, and we'll do the root 75. We'd like to simplify that root. Now, first of all, you could just type it into your calculator, and if you did root 75, it would turn out to be something like, 8.49623, da 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 da. I just made that up. That's not accurate. But it's 8 something. So, but I don't want a decimal. I want to simplify it. So how do you simplify a root? What's the procedure? What?
Use square root. Well, first you look for your square number.
Yeah, so we have to look. Wait, go ahead, keep talking.
And see if any square number goes into it.
Absolutely, that's what you're doing. You're wondering, does any square number go into 75? So you look at your list of square numbers, which you tattoo on your arm or write down on a piece of paper, and you look at where 75 would be. If 75 would be right here between 64 and 81. And then you start working your way to the left, dividing by each and every one of those to see which one goes in clean. So 75 is not divisible by 64, 49, or 36. But it is divisible by 25. That's the first square number that goes into 75. So you rewrite 75 as 25 times 3, which is just a fact you got from your calculator. If you're sitting there doing 75 divided by 64, that's a decimal. 75 divided by 49, that's a decimal. 74 divided by 36, that's a decimal. 75 divided by 25 is 3. So now you have your fact here. 75 is really 25 times 3. You split that into root 25, root 3, and then the square root of 25 is a nice, clean square number that you can actually square root, and you get 5 root 3. And we say that that's simplified. You'll need this technique when you simplify solutions from the quadratic formula. Because just look at the quadratic formula, It's negative b plus or minus the square root of b squared minus 4ac all over 2a. This square root right here is begging to be simplified. So once you actually type in b squared minus 4ac and compute it, you're going to get some sort of number, like perhaps root 75. And so at that point, you would want to be able to simplify that down. And then, so that's why we learned how to simplify a root. Chelsea?
Can you go over that one more time? So you're looking through your root numbers to see which one is divisible by 75. And
You're looking at your square numbers to see what's the first square number that goes into 75.
Okay.
Working to the left. So 75 would be here. I'm just saying, like on a number line, 75 would fall between 64 and 81. And then you just start working to the left, doing 75 divided by 64, divided by 49, divided by 36. And the first number you get to,
I didn't know where the 3 is.
oh, the 3, oh, 25 times 3 is 75. Yep. All right. Well, folks, let's take a look at what we're doing today. Today's February 6th. We get to go over section 2.6 and 2.7 today. Very exciting sections. Oh my goodness, you're just gonna love it. I already made an announcement on Monday that this is the last week for honors. So if you're interested, if you're still possible, you can come see me today during office hours right after class. Say, hey, Mr. G, I would love to research the biography of a mathematician from history and then explore the mathematics that mathematician did in depth. That sounds like a great time. And then I'll help you write the application for the honors department. And then we'd have the whole rest of the semester to meet like every other week. We could talk about your mathematician. And then by the end of the semester, you would give a presentation, a 10-minute presentation about the mathematician and about the math that they did. So maybe one of you will come see me. All right, a joke. I've got a good joke for you. Why were the ancient Romans so good at algebra? Keeping in mind, this joke is already hilarious because algebra hadn't really been around at the time of the ancient Romans, but you know, if it had been, why were the ancient Romans so good at algebra? X always equaled 10. You know, like in Roman numerals, the number 1 was I, and the number 5 was V, and then the number 10 was X. So in Roman numerals, X is the number 10. Huh. All right. So at the very end of class, we got here, right? We were just starting to do some quadratic formulas. The quadratic formula. And I think we only did what? Number 2? Sorry, number 1? And then we did which one? 7? Oh, we started 2?
And then we finished 7.
Oh, we finished 7. Okay. Well, let's just look at one more, shall we? Why don't we go ahead and look at number, well, you can choose 8, 9, or 10. Anyone drawn to 8, 9, or 10? Let's do 10. So, taking a look at number 10, we have 6x squared minus 12x plus 2 equals 0. And we've learned a lot about quadratics. So let's really bring everything that we know to bear on this problem, all right? First of all, what is the shape of this quadratic? It's parabola. Is it facing up or down? Up. And how many x-intercepts could there be?
1, 2, 0, 1, 2.
Yeah, there could be no x-intercepts if it's floating up above. There could be 1 x-intercept if it's resting on. Or there could be 2 x-intercepts if it's down below. Right? So these are all just kind of things we know in general about parabolas and what this could look like. What we also know is that if we call this thing f of x, the fact that it's set equal to 0, so this is f of x equals 0, when we're all done solving for x, we just found the x-intercepts. We just found the x-intercepts, right? Because anytime you have any function and you set f of x equal to 0, then you just found the x-intercept, right? So that's what we're doing in this problem. We're setting some quadratic, some function equal to 0, which means fundamentally we're solving for x-intercepts, which is why it's relevant to say, well, how many x-intercepts could there be? There could be 0, there could be 1, there could be 2. So now we say to ourselves, all right, well, I'd like to solve this thing. And you essentially have 3 options. You can either factor, and that's why we want to know those factoring techniques. You could use the quadratic formula, which is what we're about to do. Or if you're really excited about it, you could use a technique called completing the square. which we're not reviewing in this class. But it's just one more technique for solving a quadratic. That's basically it. You've got those 3 techniques for solving a quadratic. Except, of course, for the 4th technique, which is graphing. Right? But graphing, you can solve any equation, whether it's a quadratic, a cubic, or anything else. Graphing will always give you the x-intercepts, which will always give you the solutions to this equation. So first, let's look at factoring. Right? Factoring is kind of our first go-to, because if you can factor it, factoring is pretty quick and snappy. You know, if you can just say 1 multiplies to make 12, it has to make 8, bueno, you're done. So can we factor this thing? First of all, is it a 1x squared? No. Can I factor up to 6? No, because 6 doesn't come out of a 2. So the best I could really do is factor out a 2. But even if I did factor out that 2, leaving behind 3x squared minus 6x plus 1, that would leave us with what technique? The what?
First.
Yeah. Not the first one, because it's not 1x squared. Not the second one, because we can no longer, we already tried factoring everything out, but it didn't result in 1x squared. It might be, I mean, there's only 3 terms, so it's not grouping. But so it's just the regular long method, where the first term is not 1, so we'd have to go through this whole process. So let's just see, is it possible? If I multiply 3 times 1, that gives me 3. My factor table of 3 is just 1 times 3. Is there anything that multiplies 3 that has to make 6? No. So you see we're completely stuck. We cannot use factoring. In this particular case, factoring is not an option. So it's nice to have a backup plan, which is the quadratic formula. Now, the quadratic formula, you can either use the original numbers that you have. So you could use a equals 6, b equals negative 12, or c equals 2. But as we just pointed out, you can factor out a 2. And if you did factor out the 2, then that leaves you at 3x squared minus 6x plus 1. And now all of your numbers are smaller. And that's wise. You know, why not use smaller numbers instead of bigger numbers? So anytime you're about to do the quadratic formula, you might as well check to see if you can factor out a number, because that gives you smaller numbers to work with. All right, so when you do the quadratic formula, I would highly recommend you always write down, and by the way, you know how it's always x equals negative b plus or minus square root of b squared minus 40c? We all could be a little more sophisticated and write x intercept equals. You know, just remind ourselves, that's what we're really solving for, is the x-intercepts. So we write down the quadratic formula empty, negative b plus or minus the square root of b squared minus 4ac all over 2a. And then we go about plugging in those nice small numbers that we found. 3, negative 6, and 1. So b is negative 6, b is negative 6, a is 3, c is 1, a is 3. And at this point, I hope you all compute this arithmetic problem painfully slowly, 1 step at a time. Don't make any mistakes. Negative 6 is positive 6. And then plus or minus the square root of negative 6 squared is 36. And then minus 12, 4 times 3 is 12, all over 6. So again, that's all I ever do in my first step. I figure out what the sign is really on that first number, and then I do my 2 computations. I don't subtract yet. I wait to subtract until right now. Now I have 6 plus or minus root 24 all over 6. And at this point, again, we really need to be careful. A lot of people might look at the 6, 24, and the 6 and say, hey, they're all divisible by 6. We can divide a 6 out of all of them. But you cannot divide anything out of a square root, because a square root is a separate entity. You can't just go dividing a 6 out of the 6 and the 24, because the 24 is under a square root. So that's protected. What we need to do is bring some of that number outside, which is why we simplify a root in the first place. By simplifying root 75 down to 5 root 3, now the 5 is open for simplification. So how do we simplify root 24? We go somewhere else, do a little scratch work, root 24, and then we say again, find 24 on your square number line, and start working your way to the left. What's the first square number that goes in the 24? 4. So we can rewrite 24 as 4 times 6, split that into root 4, root 6, and the square root of 4 is a nice clean square rootable number, so it's just 2 root 6. So now we have 6 plus or minus 2 root 6 all over 6. Now there's still one last thing to do. The reason we simplified this root 24 was to get a whole number out front, because now these whole numbers can all be simplified against each other. So the 6, 2, and the 6, what can we divide out of each of those? Yeah, 2. Not this root 6, because that's underneath the square root sign. That's separate. You're going to leave it alone. But these whole numbers are all simplifiable. The best practice is to look at your 6 plus or minus 2 root 6. Just watch and see how you would do this. If I gave you 6 plus 2x, what would you do to factor? You would take out a 2, leaving behind just like that, right? So this case is no different. What we have instead is 6 plus 2 root 6. So I'm still going to bring out a 2, leaving behind 3 plus 1 root 6. Okay? So does everyone see that the fact we can treat this root 6 like an x? Right? If you had 6 plus 2x, you would take out a 2, leaving behind 3 plus 1x. A root 6 is like an x in that you can't touch it. You factor out the whole number in front of it. So you factor out the 2, and then you have 3 plus 1 root 6. And so that's what we'll do here. We can take out a 2 from the numerator, 2 outside of 3 plus or minus 1 root 6. And then all of that is over 6. And then what can you do? Now you can simplify the 2 and the 6. So 2 goes into 2, 2 goes into 6, so 2 goes into 2 once, 2 goes into 6 3 times. And we have our final answer of 3 plus or minus root 6 all over 3. And that is as simple as it gets. Right? You've hacked away all the big numbers, and really, truly look at it. You've got 6 plus or minus root 24 over 6 versus 3 plus or minus 6 over 3. So the numbers are all smaller, and that's why we learn these simplification skills, because you can break down a number, a quantity, using smaller numbers. Questions about all that? Now, folks, I want you to know that emotionally, I empathize with this feeling. Like, maybe you look at this and you think, ugh. Right? I mean, that's possible. You know, not that any of you feel that way, right? But it's possible that one might look at this and think, ugh, look at barf, look at all that. I mean, after all, this looks like the hard part, and yet how quickly did we finish the hard part? Just a couple steps, and we're to here. And now all of a sudden, just going from here to here looks like it takes as much work as simplifying the entire quadratic formula in the first place, right? So just doing the quadratic formula is not enough. You then have to do this simplification skill. And my only response to that is, yep, that's what you got to do. That's how it gets simplified. So you might think of this as like phase 1, plug in your numbers and reduce, and then phase 2, simplify if you can. And in phase 2, you have to simplify the root, factor out any common whole numbers, and then simplify with the denominator. Okay, well, really, would anyone like to ask a question or share a feeling? Beth?
I have a silly question.
I love silly questions.
Because everything gets mixed up, I guess. But why can't you just cross out the 2 6s? The 6 on the top.
Just cross out the 2 6s?
Yeah, because they cancel each other.
That is a wonderful question. Is anyone else tempted? Like, come on, let's cancel out those 6s. Well, the best way to always approach a question like that is to go ahead and see if it would work. Like, let's take a simpler one. 6 plus, we'll do 18 over 6. Right? Because we actually know the answer to this. We know what 6 plus 18 over 6 is. 6 plus 18, we can just add those. That's 24 over 6. And 24 divided by 6 is 4. Okay, we're absolutely convinced that whatever this thing is, it's equal to 4, and we know it. So now, Beth, let's simplify that. And now we have 1 plus 18 over 1, which is 19 over 1, which is 19. Is that equal to 4? No. So that's why you can't do that. Because if you just think of another example, it doesn't work out. You don't end up with the same thing.
Before you do the one part of the equation, whether it's the numerator or denominator, the rest of the equation.
Right, absolutely. And even more fundamental, Beth, thank you for asking the question. Fundamentally, the only time you're ever allowed to simplify things from the numerator and the denominator is if it's written as a product. So watch this, folks. Let's say that you have a fraction, and what you really have written down is, say, 2 times 5 times 7 times 13. And then in the denominator, you have a 5 and a 13. Everything is a product. So the whole numerator, product. The whole denominator, product. You're just multiplying. In that situation, anytime you see anything on top and bottom, you get to cross it out. And you're left with 2 times 7 is 14. So when are you allowed to simplify a fraction? Only if the whole darn thing is a product. What if I change this now and wrote 2 plus 5 plus 7 plus 13? All over 5 plus 13. Can I now cancel out the 5 and the 13? Definitely not. And how could you convince yourself? Well, just answer the question the first way. This is going to be 27 over 18. And now if I go ahead and say, replace that with a 1 and a 1 and a 1 and a 1. Now I have 2 plus 7 is 9, 10, 11 over 2. And 27/18 is not equal to 11 over 2. So the only time that you can cancel top and bottom is if everything is being multiplied. One more caveat there. Keep in mind, when I say everything is being multiplied, that does allow for situations like this. X plus 2, or x plus 3, x minus 5, all over x plus 4, x minus 5. So is everything being multiplied? Technically, yeah. I realize that I see some pluses and minuses in there. But fundamentally, we got a thing times a thing. And on the bottom, we got a thing times a thing. And therefore, you can cancel out the x minus 5s. Whereas, if we had, let's just go like this now. Now can we simplify? Nope, suddenly we cannot. Because now this is an addition problem, not a multiplication problem. Which is kind of where, this whole discussion of translating an addition problem into a multiplication is so fundamental. The difference between addition and then multiplication allows all sorts of techniques to either be used or not used. But did that answer your question?
Absolutely.
Okay, but okay, so that was a lot more than you asked for probably, but it's very helpful to know. All right, thank you, Beth. Anyone else? Chelsea? We are. It's not going to be on the first test, so I might hold off until next time, but let's see what happens at the end of class. All right, everybody, we're in section 2.6, which is so interesting. 2.6 is so interesting. So let's turn on over to here. And first of all, these notes that you get, these notes are produced by the Moore software. They go along with all the problems that are done in the program. And I know that they give notes right up front. And sometimes I feel like these notes are really well said, and sometimes I think the notes are not very well said. So in particular, we're not going to read those notes first. I just want to go ahead and dive in and show you some of these problems. And after the fact, if you want to go back and read the definitions, you can. But I would just like to talk to you about these two problems here. So let's start with number 1. What we have here is the absolute value of 3x minus 5 is less than or equal to 4. Now, remind us, what does absolute value mean again? It's your distance from 0, okay? So I want you all to imagine, first of all, as soon as we're talking about distance from 0, might as well draw a number line. So we have our number line, and we're saying our distance from 0, so I'm just going to color that up. We're saying whatever's under my hand, its distance from 0 is less than or equal to 4 units away from 0. So this object right here under my hand, where could I place it on the number line? So I'm just going to put a 4 and a negative 4 here. Could I place it here? Is that less than 4 units away from 0?
Yes.
It's less than 4 units away from 0. Could I place it here?
Yes.
That's less than 4 units away from 0. Could I place it here? Yeah. Could it be this number? Could it be this number? Yeah. Could it be any number right here? Yeah. All those numbers that I just shaded are all less than 4 units away from 0.
So in curiosity, what is the number that has a value? So would negative 4 still be a limit?
Yeah, it's still part of it. So let's talk about the number 4 as well. Could I be at 4? If I'm at the number 4, am I less than or equal to 4 units away from 0? Yes. And what if I was at negative 4? Am I less than or equal to 4 units away from 0? Yeah. So basically, I just shaded the whole solution space for whatever this thing could be. Whatever this thing is, it has to be less than or equal to 4 units away. Karis, did I answer your question? Okay. So now, what are we saying then? We're saying that this object, 3x minus 5, it either has to be less than or equal to 4, or it has to be greater than or equal to negative 4. Right? Those are the two possibilities. If I drew this again, I'd say, well, this thing has to either be greater than or equal to -4, or it has to be less than or equal to +4. And in fact, that's what we're going to write down. We're going to say that 3x minus 5, okay, considering the part on the left, had better be greater than or equal to -4, or, big or there, or it better be less than or equal to 4. And that's it. You now have two separate inequalities to solve, and you solve for x, and that will be our solution space. Now, before I keep going, who remembers what the shape of the absolute value graph is? It's a V, right? How many possible solutions could we have?
0, 1, or 2.
0, 1, or 2, right? So that's why a problem like this naturally lends itself to two equations, because theoretically, we're going to have two answers, provided that the V is down below the x-axis. So anytime you're dealing with an absolute value equation or inequality, you should expect that you're going to actually be solving two things, because you could, at most, have two solutions. So now that we've done this, let's go ahead and solve. So 3x minus 5 is greater than or equal to -4. I add my 5 over. That gives me 3x is greater than or equal to 1. I divide the 3 over. And that gives me x is greater than or equal to 1/3. So that's one solution for x. That's one thing that x could be. Or on the other hand, I add my 5 over. And that gives me 3x is less than or equal to 9. Divide 3 up. And now I have x is less than or equal to 3. So watch what we're about to say. We're saying that if I want 3x minus 5 to be somewhere between 4 and -4, then that means I need x. And that means I need x to be bigger than 1/3. I'm going to start shading that way. But I also need x to be less than or equal to 3. I'm going to shade that way. And so where overall am I shading my number line now? Just between 1/3 and 3. That's what we're saying x has to be. Okay, x has to be somewhere in this interval from 1/3 to 3. So we go ahead and write down the interval, 1/3 to 3. And this is what we would say. We'd say, provided that x is a number between 1/3 and 3, then 3x minus 5 will be somewhere between -4 and 4. So my 3x minus 5 is a number somewhere in that interval. So really look at, because this is complicated, it's complex. You have two different number lines that you're thinking about. Provided you choose any number for x between 1/3 and 3, then the value of 3x minus 5 will be anywhere between 4 and -4. That's what you were really saying. So just try it. Somebody choose a number between 1/3 and 3, a real easy number. 2 is wonderful. Let's try 2. If I plug in 2, then 3 times 2 is 6, 6 minus 5 is 1, and the absolute value of 1 is really just 1, so is 1 less than or equal to 4? Yeah. So, and you can just keep going. You can keep choosing any number between 1/3 and 3, including 1/3 and 3. Take that number, plug it in, you're going to get a true statement. Somebody choose a number not in between 1/3 and 3 and make it easy. Which number? 4. Yeah, or 0. Both of those would be just fine. I'm going to choose 4. What if I plug 4? 3 times 4 is 12. 12 minus 5 is 7. The absolute value of 7 is 7. Is 7 less than or equal to 4? No. So that's basically how this problem works, is that provided you choose a value for x between 1/3 and 3, then 3x minus 5 will be somewhere in between 4 and -4, which is what we want. Chelsea?
So is this like solving for the domain and range, or
Yeah.
would you be answering it with either a bracket or?
Exactly. We are, and in fact, we're going to give you instructions. Solve and write your answer in interval notation. So the solution is 1/3 to 3. Any x value between 1/3 and 3 will provide us the answer we're looking for. Okay, I'm going to show us one more using the conceptual understanding of what an absolute value means. Let's look at number 2. So in number 2, we have the absolute value of 2 minus x. And then minus 4 is greater than or equal to -3. So first of all, who remembers what we have to do before dealing with an absolute value expression?
Isolated.
Isolate, yeah, I heard like 3 people talk at once. I think everything that you all said was correct. We need to get the absolute value all by itself. And right now it's not all by itself, it's being subtracted by 4. So let's move that 4 over. And now we have the absolute value of 2 minus x is greater than or equal to 1. So now we can actually begin our analysis of this figure. And what we're saying, again, is distance from 0. Whatever's underneath my hand, I want that to be a number that's more than 1 unit away from 0. So I'm going to draw a number line. I'm going to say here's 0. And where is 1 or more units away from 0? We can go ahead and put 1 and -1, because that represents the boundary of being at least 1 unit away from 0. So where could this number be? It could be over here, or it could be over here, right? I mean, anywhere out there is going to be more than 1 unit away from 0. And what about 1 itself? Is 1 greater than or equal to 1 unit away from 0? Yeah, and what about -1? Is that equal to or greater than 1 unit away from 0? Yeah, so what are we shading? That. This is what we're saying I want 2 minus x to be. I want 2 minus x to equal any number over here or over here. That's what I want the number 2 minus x to be. So now we create 2 different inequalities. What are we saying? On the one hand, what am I saying? I want 2 minus x to be less than or equal to -1. So I want 2 minus x to be less than or equal to -1, right? Because I'm shading to the left. Or I want 2 minus x to be greater than or equal to 1. There we go. And that's our 2 different inequalities that we'd have to solve to get our 2 different potential answers for x. So away we go. I'm glad that we had this one because this can often be tricky. We have 2 minus x. We want to solve for x. Well, technically, there's a 1 in front of that x, so you might as well write it in there. So algebraically, what's happening? X is being multiplied by -1 and adding by 2. So we'd have to subtract off that 2 first. That leaves us with -1x less than or equal to -3. Now, x is being multiplied by -1, so we'd have to divide by -1. But what happens when you divide by negative? You have to flip the symbol. You have to flip that inequality symbol, so now it's greater than or equal to 3. So there's our first part of the solution, is that if we want 2 minus x to be somewhere over here, then x had better be a number bigger than or equal to 3. Now, on the other hand, what about this one? 2 minus 1x is greater than or equal to 1. So again, algebraically, x is being multiplied by -1 and adding 2, so we subtract 2. Now we have -1x is greater than or equal to -1. X is being multiplied by -1, so you divide by -1. And we just divided by a negative, so we have to flip the inequality symbol, and negative divided by negative is positive. So notice what we just found. If we want 2 minus x to be over here, x would have to be bigger than 3. If we want 2 minus x to be over here, x would have to be less than 1. So let's put these 2 pieces of information together. I want now a new number line to talk about x. This number line was talking about 2 minus x. This number line is talking about x. I either want x to be greater than 3, greater than or equal to 3, or I want x to be less than or equal to 1. And that's what we're saying we want x to be. And so what's our interval notation here? Negative infinity, positive infinity. Our interval will be using the union symbol. So our interval solution now is from negative infinity to 1, oh, with a bracket, 1 has a bracket. Union from 3 to infinity. Notice what this is saying. If you choose any number from this interval, then 2 minus x will be in this interval, which means if I choose any number from here and plug it into this original equation, it'll be true. So who wants to try it? Somebody choose a number over here from this interval, from negative infinity to 1. Choose a nice, easy number. 5? 5 is not in this interval, from negative infinity to 1. Negative 5 would work. So I'm going to plug in negative 5. 2 minus negative 5 is really 2 plus 5, which is 7. The absolute value of 7 is 7. 7 minus 4 is 3. And 3 is greater than or equal to negative 3, so that's true. Someone choose a number from over here. 5 works that time. So 5, 2 minus 5 is -3. The absolute value of -3 is 3. 3 minus 4 is -1. -1 is greater than -3. So, provided you choose a number from this interval, then the original inequality will be true. Okay. Now, we solve these problems conceptually, using a full understanding of what absolute value means. I just want to throw out to all of you that, like you, I was taught a purely mechanical method for solving these. And it is helpful to just memorize the mechanical way of doing this. And that is that when you have an absolute value inequality, 3x minus 5 less than or equal to 4, what you can do is just write down this. You're going to break into 2 equations, 2 inequalities. The first time, you just write it down exactly like it is, but you drop the absolute value. So 3x minus 5 is less than or equal to 4. The second time, you again drop the absolute value. And what you do is you flip the symbol, change the sign. And that's just a purely mechanical routine that you can memorize and tell yourself to do. You know, just kind of bypassing all of that pesky concept of what we're talking about. That's just how you solve it. So if you want to solve any absolute value inequality, you drop the absolute value signs, and then you keep what's there, less than or equal to 4, or you change the symbol, change the sign. And then those are what you solve. So just in case that's helpful to you, to just memorize this is the procedure. It will lead to the same result. But of course, I hope that you understand all this. You know, that's the real goal, is to understand why we do that. That's just a routine. This is why we do that. All right. We have a couple more problems here we can practice, which I think let's go ahead and do. How about we just do one of those? Oh, no, actually, we're going to do both. Everybody, go ahead and try number 3 on your own right now. And if you like, use that rule I just told you. Go ahead and try number 3. You're going to start off with 3x plus 5, and then plus 2 is less than 1. Oh, you know what? I believe this is a trick question.
Yeah.
Yeah, this is a trick. How did you know it was a trick question, Josh? Yeah, so I mean, let's just look at it. If you move the 2 over, and you have 3x plus 5 is less than -1, then your distance from 0 be less than -1. You know, your distance can only ever be positive. You can only, like, my distance to Abe, you know, is 2 feet, or you know, whatever. So my distance to somebody can't be a negative quantity. So since there's no solution here, what does that imply our graph looks like? That means that the absolute value graph is floating up above, right? That there is no x-intercept, and therefore there is no solution. Yep, your answer is just no solution. And just to show you all what that looks like, if you have absolute value of 3x plus 5, there we go, and then let's see, it's plus 1. There, this is the graph, and indeed, it's floating up above the x-axis. There are no x-intercepts, and therefore, there's no solution. So in other words, there's no number in the universe that I can plug into that inequality to make it true. Okay, the last one is genuinely different. Let's do that one together. It says 1 is less than the absolute value of 2x minus 9 is less than or equal to 3. Again, I think concept here is very helpful. What are we saying about this thing? Let's draw a number line. What do I want this thing's distance from 0 to be? How far away from 0 do I want to be? More than 1. I want to be more than 1 away from 0. So first of all, here's 0, here's 1, and I want to be like greater than, strictly greater than. So I'm going to be more than 1 unit away, or more than 1 unit away that way. Okay, so I want my distance from 0 to be more than 1 unit away, but I want to be less than or equal to 3 units away. So on my number line here, this is what I'm saying. Everybody just look at that number line and see, you know, if this makes sense. You know, you could think about a teenager who wants to get away from home, like this is their home, and they're like, hey, you know, I'm rebellious, I want to be away from my home, but not too far away. because they can be scary, right? So if this is your home base, you want to be away from home, at least 1 mile away from home, because that's cool. But you don't want to be more than 3 miles away from home because you could get trouble, right? So that's where we're saying this person could be. Is more than 1 mile away, but less than 3 miles away. So where could that person be? Anywhere in this region. But keep in mind, that's what we're saying 2x minus 9 is. 2x minus 9 could be any number in here, and 2x minus 9 could be any number in here. So now you would have to proceed to solve that. So let's solve this one first. We're saying 2x minus 9 would have to be less than -1, but more than -3. That's one possibility. Or we're saying that 2x minus 9 would have to be more than 1, but less than 3. Yes, Paris.
It's less than or equal.
Oh yeah, thank you. That would have to be greater than or equal to 3, and then that would have to be less than or equal to 3. Yeah, very good. Okay, so now you'd end up solving both of those. Now this is a compound inequality. We're solving for x, and whatever you do it to both sides. So here x is being multiplied by 2, it's subtracting by 9. So we'd add 9 to all 3 bits. And that cancels out. Now we have 2x is less than 8, but more than 6. That's how a compound inequality works. You do your action step to all 3 parts. And now x is being multiplied by 2, so I divide by 2 on all 3 parts. And now I know that x has to be less than 4, but greater than or equal to 3. So that's one part of the solution, that so long as I choose a value of x between 3 and 4, then the value of 2x minus 9 will be between -3 and 1. -3 and -1. So now we have to go over here and solve this one. So same thing. We add 9 to both sides. It's all 3 sides. And now 2x is less than or equal to 12 or greater than 10. X is being multiplied by 2, so you divide by 2. And now we know that x has to be less than or equal to 6, but greater than 5. Now we can write down our solution for what can x be. On the number line, x could be between 5 and 6, open circle, close circle. Or between 3 and 4, close circle, open circle. And again, the logic states, so long as you choose an x value between 3 and 4, between 5 and 6, then 2x minus 9 will be between here or here, which means the absolute value of 2x minus 9 will be between 1 and 3.
And how do you write the interval notation?
So then the interval is just these 2 intervals right here. So that would be from 3 to 4, union 5 to 6. Folks, I'd like to tell you some good news, that you're not going to have a problem like that on the test. Is that happy? But this was a good problem. I mean, this is really getting into the depth of how we even use symbols and how to walk your way through a fairly tricky conceptual problem, right? This is a fairly tricky problem. I have no doubt that for the most part, at least everybody's brain should have hurt a little bit in that process, right? But the more you do these kind of problems and walk your way through that complex thought, the better at it you're going to be. So what can you actually expect on the test? Well, whatever's on the practice test. You all have the practice test already, but it's going to be more of like a problem like this. Ready? Okay. We are now ready to do some quadratic inequalities. Quadratic inequalities, if I do say so myself, are a whole lot more fun and very interesting. So let me start by facing my board here. Now, would anyone like to ask anything before we move on? Again, the practice test, I posted a blank copy on Canvas announcements, as well as the solutions. So at any point this weekend, you can go home, print up another copy of the practice test, print out my solutions, look at my solutions, look at your practice test, take the practice test once or twice, and email me any questions that you like. Make sure you email me. I'd be happy to help you. All right, well, everyone take a look at the setup there. It says, when we ask if f of x is less than 0, we want to know when the graph is blank. And when we ask if f of x is greater than 0, we want to know when the graph is blank. Let me answer that question. What do we even mean by f of x is less than 0 or f of x is greater than 0? What does that mean? So for instance, if I just say, I want f of x less than 0.
The function.
Yeah, the function is less than 0. What does that mean? Well, first of all, I'm asking you to, let's come up with a meaning behind f of x less than 0 and f of x greater than 0. We already know the meaning behind f of x is equal to 0. Right? Don't we all know what that means? What does f of x equal mean? It's the x-intercept, right? So I'm just going to draw the same parabola over and over here. So when I ask the question, when is f of x equal to 0, I'm asking for my x-intercepts, right? And furthermore, what does f of x represent again? If I have a function, f of x equals, I'll just do something simple like 3x. And then I have an input, and then I have an output, right? And so every coordinate in space is either x comma y, or input, output, or another way of thinking about it is f comma f of x. So what does f of x represent? Well, not the y-intercept, but the y coordinate, right? F of x is the y value. F of x really truly is the y value of any given coordinate. So when we say we want f of x to equal 0, what are we saying about this coordinate right here? What about it is 0? The y value. And what about this is 0? The y value, right? So when we say we want f of x to be equal to 0, we're talking about when is the function on the x-axis. So we could say f of x equals 0 is asking when is the graph keyword on the x-axis. Okay, that's my lead-in now for you to figure out the second one. Don't shout it out just yet. What do we mean f of x is less than 0? You have all the clues on the board that you need to think about this. What is f of x again? The y value of the coordinate. And less than 0 means that that number is less than 0, which means that number is negative, a negative number. And where are y values negative? Down here, right? So what are we asking? When is the function
Below.
below? That's what we're saying. When is the graph below the x-axis? Keyword below, which hopefully that keyword goes really well with less than, because if you're less than something, then you're below it. So when is it below the x-axis? And I'll even graph this now. When is it on the x-axis? Here and here. When is it below the x-axis? There. That shaded bit right there is when f of x is less than 0. Okay, so then everybody, when is f of x greater than 0? What are they meaning? Above. When is the function above it? And so now we're talking about here and here. So when is the function, or when is the graph above? And above. I should have written that nice and big, above. So just to throw in some concrete examples, so this is very obvious. F of x is the y value. This coordinate right there. This coordinate right here is the coordinate 3, -2. Is my y value negative? Yeah. F of x is less than 0. The y value is less than 0. The y value is negative. Sure enough, the y value is negative because that coordinate is below the x-axis. What about here? If I choose this coordinate right here, that's the coordinate 8, 6. 6 is positive. Is f of x greater than 0? Is the y value positive? Yes, it is. And in fact, all of these coordinates, the y value is positive. And then all of these coordinates, the y value is negative. And just these coordinates, the y value is 0. So there we have it. I hope that makes sense. So did you all write it down? When we ask f of x is less than 0, we want to know when the graph is below the x-axis. And when f of x is greater than 0, we want to know if the graph is above the x-axis. And that's it. These problems are best solved using a graphing calculator. So everybody, we're going to do these first few using a graphing calculator, and we can just report our answer when is x squared plus 2x minus 3 greater than or equal to 0. So I'm going to plot our x-intercepts right here. Everyone, you have the graph right there to look at. Go ahead, and this is number 7, right? I want you to make a graph. So on number 7, you're all going to make a little graph and make an x-intercept at 1 and make an x-intercept at -3. And then draw your parabola. Because first of all, that's what the graph looks like. And now we're asking, when is x squared plus 2x minus 3 greater than or equal to 0? So what's the keyword we want to know? When is this function
Above?
above the x-axis? Yeah, greater than 0, but when is it above the x-axis? So we're asking, when is that function above the x-axis? So if you have a different color, you could color or shade the tails that we're interested in. We're interested in those tails right there. So when is the function above the x-axis? Well, now, first of all, it's above or equal to. So we are including this point. We're including the x-intercept and above it, right? Because it's greater than or equal to. So we're really saying above / on the x-axis. Perfect. So now we write our answer in interval notation. So according to the x-axis, what part of our graph are we interested in? Anywhere to the right of 1. So from 1 to infinity. From 1 to infinity to the right, that's my first chunk of interval. And or anything to the left of -3. So that would be -infinity to -3. And that's it. That's our answer. The answer is, when is x squared plus 2x minus 3 greater than or equal to 0? Well, for any x value that you choose in this interval, if you plug it into that quadratic, your answer will be positive or equal to 0. So somebody pick a number. Pick a number from this interval. Pick any number from this interval. Make it easy. That has to be between 1 and infinity. 2. Well, which one? 2 or 3? Okay, 2. Everybody, let's watch what happens when I plug in 2. I would have 2 squared plus 2 times 2 minus 3. And so that's 4 plus 4 minus 3, which is 8 minus 3, which is 5. Is 5 greater than or equal to 0? Yeah. And that's all we're saying. That's all we're saying. We're just saying, for what x values will this function be greater than or equal to 0? For these x values. Any x value from this interval, you're going to be able to plug it into that function, and it will, in fact, be greater than or equal to 0. Okay? Let's try the next one. 7, 8. Oh, P.S. How could we have done this if we didn't have a graphing calculator? Now, first of all, you all have graphing calculators. Can you use your graphing calculator on the test? Yes. So can you solve it this way? Yes. But let's just say you're on a desert island, right? You're on the show Lost. You just crash landed. You're like, oh no, we need to solve some quadratic inequalities. What are we going to do? You can factor this. So watch this. I'm going to factor x squared plus 2x minus 3. And so what multiplies to make 3 that adds to make 2? Well, my factor table is just 1 times 3. It would have to be -1 and +3. So now we have x minus 1, x plus 3. And what you do is you just temporarily say, what if we're setting it equal to 0? My x-intercepts would be x minus 1 is equal to 0, or x plus 3 is equal to 0. And therefore, x equals 1 or x equals -3. Those are my x-intercepts. Were those my x-intercepts?
Yes.
Mm-hmm. And what does my parabola look like? Facing up. So from this technique, I would just put an x-intercept there, an x-intercept there, and I can just draw my parabola. So did I really need a graphing calculator? No. You can do this on your own. You can take your function, factor it, find the x-intercepts. You just know that it's parabola facing up, so you just draw it, and then you do the same thing. And you say, when is it above the x-axis? So just for fun, let's try number 8 without graphing it first. And then graphing it, well, okay, this one we have to factor. So we have 3x squared is less or equal to 11x plus 4. Golly, I hope this one's factorable. It is. So, first of all, this is not a question we can answer. What do we have to do? What's that? We need to move all of our terms over to the left, because we can only answer questions less than 0 or greater than 0. So let's go ahead and move all of our terms to the left. We're going to subtract 11x from both sides, subtract 4 from both sides. We're moving all those terms to the left. So now we have 3x squared minus 11x minus 4 is less than or equal to 0. So what question are we asking? When is this graph less than, which means below? When is the graph below the x-axis? So we're asking, when is the graph below the x-axis? So if you want to write this down, you can. But just, to really apply and practice this whole concept of factoring, we have 3x squared minus 11x minus 4. I can't factor out a 3, so I have to do the long technique. 3 times negative 4 is negative 12. I write my factor table 1 and 12, 2 and 6, 3 and 4. I want to know which of those adds up to negative 11. It would have to be 12, where the 12 is negative and the 1 is positive. So now I rewrite the middle term, 3x squared minus 12x plus 1x minus 4, factor by grouping, and I pull out a 3x, which leaves x minus 4. And then this, I can just pull out a 1, which leaves x minus 4. They're both x minus 4, and so I factor it to x minus 4 and 3x plus 1. I know I did that really fast. It's just because I wanted to show you that you can, in fact, factor it. You don't have to, but you can, using the technique we were just talking about. So then I would set both of those equal to 0 to find my x-intercepts, right? So either x minus 4 is equal to 0, or 3x plus 1 is equal to 0, which means either x is 4 as an x-intercept, or, gotta do a little algebra here, x equals negative a third. So now let's graph it and see if that worked out. I just want to show you why we learned factoring. It's so that you can get the same solution that you would otherwise get by using a graphing calculator. So here's my graph, 3x squared minus 11x minus 4. And here's our graph. What are my x-intercepts? 4 and negative 0.33333. So were those the x-intercepts I got by factoring? Yeah. Did factoring take a few steps? Yeah. Would it be easier to graph it on your graphing calculator? Probably. And I'm telling you, you can use either approach, okay? You can use either approach. Whichever approach you used, this is the work I need to see on your test to give you full credit. I would now want you to draw me a little graph and get your x-intercept, what was it, at 4 or at negative a third. And you draw, first of all, the parabola, is it facing up or down? Yeah, facing up is positive. So there's my parabola. And what are we asking for again? When is it below the x-axis? So look, below or on, it's less than or equal to. So it's below / on. So that means you would shade the little happy face portion right there. And so what interval is that? Yeah, negative a third to 4.
So that's for full credit, just.
Yep, I would give full credit. Show me that you know, I know you know that you're talking about when is it below. Show me a little sketch with the x-intercepts, and you can get those x-intercepts from factoring or from your graphing calculator, either way. So long as you show me a picture of this graph, show me the x-intercepts, and then interpret it correctly. Namely, you're interpreting it that if it's below, you're doing this little smiley face, or if it's above, you're doing the tails. Notice that if it's above and you have tails, you need a union because it's 2 intervals. Whereas if it's below, it's just one little smiley face, it's just going to be 1 interval. So let's complete the logic here. What are we asking? We're saying when is this function less than or equal to 0? So what x values can I plug in here to make this thing be negative? Anything from in there, right? So somebody choose a number between negative a third and 4. Make it easy. Abe? 1. 1. Great, let's try it. If I choose a number from this interval, we are guaranteed that 3 times 1 squared should be less than or equal to 11 times 1 plus 4, I'm using the original inequality. So that's 3 is less than or equal to 15. Is 3 less than or equal to 15? Certainly it is. And the same result would be true if I chose any other number between negative a third and 4. Choose any number here, and that inequality will be true. Isn't math interesting? Okay, that's a loaded question. Maybe, maybe not. But folks, we're really, this is good stuff. Like, I just want you to know that. We're covering, this is really good material. You know, not that absolute values in and of themselves are interesting, but the logical chain of thought you have to follow to get to an answer. That's really what we're talking about in this class, is, you know, the math could be anything, but, you know, seeing how to apply a definition and make a picture of it and see where to go. This is really good material. Okay, well, let's see here. We're going to take a break because my phone went off. And then when we come back, we'll wrap up a couple more inequalities, some word problems, and then we're on our last section on regression. So everyone, let's take a break. The time is 9:09. Let's be back at 9:19. If anyone has any questions, you feel free to come up here and ask. Yes. Oh, great. Let's.
So I was using the calculator with that plus 2 minus 3.
Yeah.
But then when I go to the graph,
Very good.
I go to the coordinates are not the
Right.
exact
They are not. So first of all, if you're pushing your arrows first, it's just a floating cursor. It has nothing to do with the graph. You have to trace. Now you're actually on the graph. Okay, so now your cursor's following the graph. Now, and it's never going to land exactly.
Okay.
That's why you'd have to go above the word trace is calc. So hit second calc. Now you can do a variety of things. You can just find it. Hold on, let me show you more. So a value just means you plug in an input, I'll take the output.
Okay.
So that's simple. That's just input output. If you go to root, that's going to say the x-intercepts. Just root means x-intercept. So the way that works is they want a lower bound. That means put your cursor to the left of the x-intercept you're interested in. I'm interested in that x-intercept, so now I'm to the left of it. I hit enter. Now upper bound, that means put it to the right of the x-intercept. Now I'm to the right of it. Enter. It says guess. Hit enter again, and it tells you the root. So that root's exactly at 1. So now I want you to try that. Second calc, do the root function. Now go over here to this one. Put your cursor to the left of the x-intercept. It has to be to the left of the x-intercept.
Okay.
Meaning, once you hit enter, you'd have to push. You'd have to push to the right to get it to the other side of the x-intercept.
Okay.
And then hit enter, enter. Understand one.
Awesome.
What else do you want?
That was more, I was like, eh.
Well, this is a good time. What other graphing calculator questions do you want to ask?
I mean, that was really it. I didn't understand how to go here and figure out how to do the minimums as well. So that would just be the same thing, going down, enter, and then go above, enter, enter.
It has to be the correct order, though, again, from left to right. So wait, which one did you just try to do? You're trying to find the x-intercept?
Well, so I was going to do the minimum.
Oh, okay. So the minimum, again, you would need your cursor to be to the left of the minimum,
Okay.
and then you'd push it to the right of the minimum, and then guess. And then it will tell you your minimum is down there.
Okay.
Always to the left and then right,
Left.
just like intervals,
Okay.
left to right.
Thank you.
You're welcome.
So how come you gave us all these little, pieces of them? Is it, are
We-
you trying them separately or just spread on?
That was just practice we did. We did that all on Monday.
Oh, okay.
Yeah,
So
yeah.
we're not turning, are we turning these
You
in?
don't turn in the ones that were just extras. You only turn in the ones that are chapter 1 and chapter 2.
Like this packet?
Yeah, yeah.
This packet?
Yeah, the big one, yeah, you turn those in.
That's all.
But yeah, on Monday, you weren't here, right? Yeah. So on Monday, we did those other ones.
Yeah.
And that was all kind of like a review of that material.
Oh, okay.
Bryce. Okay, I remember. You used to sit right here, but I've kind of booted you out of
Yeah,
your
it's
space.
okay.
All right. Good morning, DJ. This is JW Gabrielle. Hey, I know my mom just called you. We're going to try to bring our truck in soon, and I just wanted to share that so far as we know, the issue is that the power steering fluid has a small leak, and there's some sort of a small leak also in the oil pan. So those are two separate issues. All right, thank you so much. I think she'll be bringing it by sometime today. Okay, have a great one. Bye-bye. All right, folks, it's 9:19. Let's keep going. We're not going to completely do number 9 and 10. Let's just look at them real quick and confirm that we agree on how to approach them. So in number 9, we have x squared plus 9 is less than 6x. So how do we begin the problem? What do we need to do? Yeah, we have to move all the terms left. Move terms left. Because we really only know how to interpret f of x is less than 0, f of x is greater than 0, right? Below the axis, above the axis. So first, we have to move everything to the left. And so we have x squared minus 6x plus 9 is less than 0. And so already we know we're talking about what? Below or above? Everyone agree? Below? Yeah, less than means below. So we want to know below, and this is strictly below. It's just less than 0. So we're no longer talking about the x-intercepts. We just want to know when the graph is below, right? And plus, what's the shape of this parabola? It's facing up. So we can already kind of imagine what this should look like. It's going to be some sort of parabola. And we're interested in, not the x-intercepts, I put open circles there. We're interested in this part down below, right? So I want you to notice, I haven't done the problem yet. I haven't factored it. I haven't looked it up on a graph, but I already know what the answer looks like, right? That's important. That you're just kind of imagining, hey, this is what the answer is going to look like. That I'm going to find two x-intercepts. I'm looking for the part that's below the axis. Now I just need to fill in the numbers, right? So you could graph it, and by all means you can graph it on the test. You can if you want to. But can we factor this? What multiplies to make 9 that adds to make 6? 3. So I'm going to go ahead and say, well, let me do my factor table. That's 1 and 9, 3 and 3. And I need it to multiply to make a positive 9. So that's plus times plus or minus times minus. I need them to add up to negative 6. So really, I need negative 3 and negative 3. Well, x minus 3 times x minus 3. Again, finding the x-intercepts, something times something equals 0. That means either x minus 3 equals 0 or x minus 3 equals 0. Actually, that means I have the same x-intercept twice. So what does that graph look like? That means I only actually have one x-intercept, which means it's sitting on the graph. So was I right about my original assumption? No, I was incorrect, right? I made an assumption, didn't I? You guys all know the word assume. You make an ass out of you and me when you make an assumption. So I made an assumption that I thought I knew what it looked like. It didn't look like that at all. It looks like this. So when is this below the axis? It isn't. Right, it isn't. Is this thing ever below the x-axis? Keep in mind, we're not interested in the x-intercept. That is the x-intercept. I want to know when is it below? It's not. So the answer is no solution. What does that really mean? It means no matter what value for x I plug in, it's always going to be positive or 0. Right? So any number in the universe that I plug into this quadratic, if I actually evaluate it, it's going to be a positive number or it's going to be 0. So will it ever be less than 0? No. So that was an interesting problem. I'm going to cross that out just so we all see that my assumption was incorrect. Okay. Then how about number 10? You have a problem like this. So 9x squared plus 16 is greater than or equal to 24x. What's the first thing we have to do? Yeah, move all of our terms to the left. Thank you, Bryce. So I'm going to subtract 24x from both sides, subtract 24x from this side. Now we have 9x squared minus 24x plus 16. And to be fair, to be honest, the first thing we probably all want to do is just graph it, right? Because by graphing it, you really sidestep the whole issue of having to factor that expression. So 9x squared minus 24x plus 16. Ooh la la, look at that. It's another one that lands on the x-axis. So my x-intercept is at 1.33333. And so is this thing ever above or equal to the x-axis? When is it above or equal to the x-axis? When is this parabola above the x-axis?
It's not.
When is it above the x-axis? Yeah, always. It's always above the x-axis, isn't it? I mean, it does touch it just once. But look at the question we're asking. We were asking, when is this function above or on the x-axis? So when is it above or on? Always. And so the answer is, the solution is any x is a solution. So what is our interval notation for all real numbers? Negative infinity to infinity. Any number at all that you plug into that thing, it's going to be positive or zero. So these two problems were kind of interesting, right? Because we're saying if you ask this question of below or above, sometimes the answer is going to be it's not. And sometimes the answer is going to be it's always. Right? So there we go. So now we have some word problems. Everybody's favorite. So we have some problems here. Now I'm for sure that a couple of these are going to be on your test. So I'm just going to leave that up there. But we're all now very equipped and confident in knowing what we're doing. Anytime you see a quadratic with an inequality sign, you're going to think, hey, I just want to know when is it above the axis, when is it below the axis. It's a very simple question. So number 11, the profit in dollars by selling X bottles of tonic, whatever tonic is. What's tonic? Do they mean tonic water? Like the soda water that has a weird taste?
Yeah.
Or do they mean a tonic, like old school medicine people who would come through town and try to sell everyone their tonic, which was really just a useless liquid? So who knows? I don't know, but it's tonic. And the profit is given by, so P of X is negative X squared plus 25X minus 100. Whereas X is between 0 and 35. How many bottles of tonic must be sold to make at least $50 in profit? We want to make at least $50 in profit. So first of all, just notice, this is our profit formula. And the profit formula is apparently only good for X values between 0 and 35. So how many bottles of tonic can you sell? Between 0 and 35. You know, maybe that's all you got, right? You looked in your grandma's attic, you found 35 bottles of tonic. You're like, hey, let's go try to sell these. Right? So that's all you have. The first thing you would probably like to do is see a picture. Always helpful to see a picture. Negative X squared plus 25X minus 100. So here's our graph. And what are we saying? How many? No, so first of all, do you see the 0 to 35? Let me fix my axes here. My axes are going to go from negative 5 to 40. So there we go. 35 is right here. 0 and 35. I mean, it's kind of funny. Between 0 and 35, it's only above the x-axis between 5 and 20. So I don't understand. Like, apparently, if you sell 35 bottles of tonic, you're actually making negative profit. So I don't know if this model of just is not very realistic or what. Well, what are we asking about our profit? We want how many bottles of tonic must be sold to make at least $50. Where's $50 on the y-axis? Up here. So watch me graph it. Y equals 50. Remember, that's how you graph a horizontal line. It's just y equals the y-intercept. So now what are we really asking? When is my profit above 50? So you see that teeny little cap up there? That's what we're interested in. We're looking at this teeny little fella. Now I can go ahead and click on this in Desmos. Between what x values must we be?
10 and 15.
10 and 15. So there we go. That's already our answer. When is the profit above 50? Between 10 and 15. How many bottles of tonic must you sell? Between 10 and 15. So graphically, that's already the answer. So you can all go ahead and jot down. The answer is between 10 and 15. And how do we write that as a interval? Is it bracket 10, comma 15? Would that be our answer? Okay, now, I almost feel like that was too easy, right? Too easy. Is it correct? Yes. Did we answer it? Yes. Do we have the right understanding? Yes. However, what if you didn't have a graphing calculator? What would you do? I want you to see how to set this up. What are we really saying about profit? We want our profit to be what? At least 50, right? So what we're saying is we want profit to be at least 50. That's what we really want. Everyone write this down with me. We're all going to write this down and do this. We really want profit to be at least 50, greater than or equal to 50, which means my whole function, negative x squared plus 25x minus 100, I want that to be greater than 50, right? I'm showing you how to do this by hand, because as always, we learn things in here, how to do it by hand, even though you can check your answer by looking at the graphing calculator. And in this particular case, this is what I'd want to see on the test, is I'd want to see you take your profit, make it at least 50. Now what do we do? Not add 100 to both sides. We always want to have everything equal to 0. So we always move all of our terms left. So let's bring that 50 over. That way we're asking the normal question of greater than or less than 0. Because remember, we have to reinterpret the problem as above the axis or below the axis. Okay, so now what? We have a leading negative. Can we get rid of it? Yeah, we want to get rid of that leading negative. So if we go ahead and factor out a -1, that would factor it out, and then we could divide it to the other side. But instead, you can also just multiply everything by -1. If you multiply everything, both sides, by -1, will that get rid of our leading negative? Yes, it will. However, when you multiply an inequality by a negative, what do you have to do? Flip the sign. So now we have, when is x squared minus 25x plus 150 less than or equal to 0? Listen, I totally admit, this is a lot of algebraic machinery that we're doing. These are a lot of things that we're doing. We're setting it greater than or equal to 50. We got to move the 50 over. Then we have to get rid of the leading negative. Now we're here. So now, what multiplies to make 150 that adds to make 25? Can we factor this to find our x-intercepts? I would make a factor table for 150. Let's say, okay, what multiplies? So 1 and 150, 2 and 75, 3 and 50, 4 and nothing, 5 and 30, 6 and 25, 7 and nothing, 8 and nothing, 9 and nothing, 10 and 15. So what do you multiply to make 150 that you can add to make 25? This one's tricky. We want to multiply to make a positive 150, which means it either has to be plus times plus or minus times minus. We want them to add up to -25, so it has to be minus times minus. So which one of these, when you add together a negative plus a negative, gives you -25? Now, this one. Notice that was tricky because you had another option up there that 30 minus 5 would give you 25, or 10 plus 15 would give you 25. So this required some very careful analysis that we're multiplying two numbers to make a positive 150, which means it's either a plus times a plus or a minus times a minus. So both signs have to be positive or both signs have to be negative. You'll notice this wouldn't have worked. -5 plus -30 is -35, which is not the middle term. So here it is. And so we factor this into x minus 10 times x minus 15. And if we call those our x-intercepts by setting them equal to 0, what do we get? 10 and 15. Is that the original answer that we had?
Yes.
Yep. So now what are we really saying? We have a quadratic. It's a parabola. It's facing up. The x-intercepts are 10 and 15. It's facing up. And we're wondering, when is this parabola what? Above or below?
Below.
Below. And so when is it below? Between 10 and 15. So again, I bet you all preferred the graphical solution we did first, because you just graph it and you look. But did the algebraic approach lead to the exact same answer? Yeah, it did. And so it's important to know both. The ultimate answer is how many bottles of tonic must be sold in order to make at least $50 in profit? Between 10 and 15. And your answer would be expressed in interval notation, between 10 and 15. All right. Let's try another one. Number 12. Suppose c of x, what does c represent? Cost, probably. C of x to x squared minus 10x plus 27. X has to be more than 0. Represents the cost in hundreds of dollars to produce x thousand pens. Find the number of pens which can be produced for no more than $1,100. So find the number of pens that can be produced for no more than $1,100. So what is 1,100? The cost, and we want our cost to be less than 1,100 or more than 1,100? Less than 1,100. So we want this to be less than $1,100. Right? Is it less than or equal to, or just less than? Yeah, no more than. So it could be 1,100, but no more. So yeah, it's less than or equal to. Okay, so now what do? We've got this nice inequality. We need it to be equal to 0. So we move our 1,100 over, and oh, 1,100, boy, that seems like an awfully big number. What is our cost in? The cost is in hundreds. So what, 1,100, what number should we actually be using? 11. That was tricky. Had you left it as x squared minus 10x plus 27 less than or equal to 1,100, and then you brought the 1,100 over, that would not have been factorable. So you'd have been stuck in this position like, oh, gee whiz, what's happening? Why can't I factor this thing? It's because we have to be very careful about our units. They're saying the cost is in hundreds. And so if the cost is 1,100, the number we put there is actually 11. Okay, so now let's do it. We move the 11 over. It says x squared minus 10x plus 16 is less than or equal to 0. So can we factor that? What multiplies to make 16? It adds to make 10. So what multiplies to make 16? 1 and 16, 2 and 8, 4 and 4. I want to multiply to make a positive 16. That means it's either plus times plus or minus times minus. And I want to add to a negative 10, which means it must be both numbers are negative. So which one of these adds to 10? Yeah, 2 and 8. So our solution is x minus 2, x minus 8. That's going to be our x-intercepts. Therefore, x minus 2 is equal to 0. X minus 8 is equal to 0. By the zero product rule, so x equals 2, x equals 8. My x-intercepts are 2 and 8. What on earth did we just find out? Find the number of pens that can be produced for no more than $1,100. So how many pens? Yeah, we think between 2 and 8, right? Let's verify. What's the shape of our graph? It's a parabola facing up, and the x-intercepts are 2, 3, 4, 5, 6, 7, 8. So yes, it is a parabola. It is facing up, and I want to know when is it below the x-axis. And when is it below the x-axis? This little smiley face shape right down here. Below or on. So you'll notice that the blue part of my graph is less than or equal to 0. It's below or on the x-axis. And therefore, what x values are we talking about? Between 2 and 8. Now, is the answer actually between 2 pens and 8 pens? No, it says x 1,000 pens. So even though the interval solution is 2, 8, that is the interval solution, 2, 8. What are we really talking about? Yeah, if you were talking in English to a friend, not an enemy, you would say between 2,000 and 8,000 pens. I was trying to be cute there, but it's very true. Like if you were talking to a friend, you wouldn't walk up to them and be like, interval 2 to 8. Now they have to go off and reread the problem and interpret. What does that mean, interval 2 to 8? If it was a friend, you'd say between 2,000 and 8,000 pens. Right? You just tell them the information. If it was an enemy, you'd be like, 2 to 8. Then you make them go reread the problem and figure it all out for themselves. Okay. The very last one, I think I'll leave that one for homework because I want to have time to get on to the last section. But I'll just help you set it up. You've got the height in feet of a rocket above the ground after liftoff is given by h of t equals that. What is that? Negative 5t squared plus 100t. And what are we saying about it? When is the rocket at least 250 feet off the ground? So what do we set this equal to? I want the height. This thing represents height. I want it to be at least 250 feet off the ground. So what will I write right here? I want it to be at least 250
Greater
feet.
than.
Yeah, greater than or equal to 250. Is that right? Do we have all of our units correct? Are any of these units in hundreds and thousands? The height is just feet. Yeah, feet off the ground, t seconds. When is it at least 250 feet? So that height would be greater than or equal to 50. And then away you go, solving the problem. So what would you do first? Yeah, bring that 250 over. And then what would you have to do?
Factor out the negative.
Yeah, factor out the 5 and factor out the negative, right? You have a leading negative. So if I factor out a negative 5 from all this, I would have t squared dividing by 5, that's minus 20, and then dividing by 5, that's... Did I factor out the negative 5 correctly? Should I just hope? Did I change the signs? It went negative, positive, negative, so it should be positive, negative, positive. So I did change the signs. Did I divide everything by 5 correctly? 5 divided by 5 is 1, 100 divided by 5 is 20, 250 divided by 5 is 50. So did I do it all right? Wouldn't hurt to really stop and double check, right, before you keep going. You know, you want to be darn sure that you have it correct. How could I check that I really did do it correctly? I can always distribute that negative 5 back in again and make sure I still have the original expression, right? So check yourself every step along the way. Okay, now, can I divide off the negative 5? And what happens when I divide an inequality by a negative? You have to flip that symbol. So now what we really have is t squared minus 20t plus 50 is less than or equal to 0. And I think I'm going to leave the rest of that for you for homework. So you'll do a factor table, what multiplies to make 50, that adds to make 20, factor it, find your x-intercepts, and you can always check your work by graphing it. I have to erase my board, so you all might as well finish that problem right now. And if you like, we can check the answer. If you want to work with your partner, you can turn to your neighbor and say, hey, what'd you get? All right. So what does multiply to make 50 that adds to make negative 20? Yeah, none of these, huh? Yeah, so if you want to multiply to make a positive 50, it's got to be a plus times a plus or a minus times a minus, and we want it to add to a negative 20, so it's got to be minus and minus, but none of those add up to 20. So can you factor it? You cannot. Not everything's factorable. So what would you have to do instead? You either do the quadratic formula, or you use your graphing calculator and you can find the roots that way. So let's just take a look and see x squared minus 20x plus 50. There's my parabola, and my x-intercepts are 2.929 or 17.071. So that didn't work out cleanly. You weren't able to factor it, but that's still a good learning lesson. If you try to factor it and you can't, that means it's not factorable. That means the answers are going to be a decimal. Now, what are we asking about again? We're saying when is that less than 0? So when is it less than 0? We're saying when is it below the axis? So it's below the axis between 2.929 and 17.071. So how would we write our answer? Between, what's it? 2.929. Oh, okay. And 17.071. Really, and it says around to 2 decimals?
Mm-hmm.
Well, let's just double check.
Yeah, 2 decimal places.
Yeah, 2 decimals. Okay, so then the actual answer would be between 2.93 and 17.07 seconds. What did we just find out? When is the rocket at least 250 feet off the ground? So can everyone imagine launching a rocket and it's going really high up in the air, and you're just saying, hey, when is it at least so high? Now I'd like you to notice that what we just solved, look at this parabola. Does that look like the path of a rocket going into the sky? No. So there's a big difference between the quadratic that you used to solve the problem and the original quadratic. The original quadratic they gave us, negative 5x squared plus 100x, does that look like a rocket flying up into the sky?
Yes.
Yeah, that's what we'd expect. And where is it above 250 feet off the ground? Y equals 250. Oops. There. When was it above 250 feet off the ground? And there. So this is the actual flight of the rocket. That purple line is 250 feet off the ground. And so when was it higher than 250? Look at the numbers. 2.929 and 17.071. Are they the same numbers? Yeah. So it's interesting to note that if you look at the equations they gave you originally, it does look like a rocket flying high in the sky above 250 feet. But when we do all this algebraic manipulation, you turn it into a different equation, a simpler equation that now does not look like a rocket flying above the sky. But it nevertheless gives us x-intercepts, which are identical to the original solutions that you would have had if you had looked at the rocket flying in the sky. That's kind of interesting, a little mind-bending, right? That you can transform an equation into a different equation that has the same solutions, even though they look completely different, right? So the green one was the actual rocket. The black one was our solution. Okay. We're on to our last section here. And what, class gets out at 10:25?
20.
10:20, okay. So we have a good half hour here. Regression. Regression. How do we use the word regression in normal, everyday English? Do we ever use the word regression? Anybody? Every once in a while, so my wife and I, we have a 2.5-year-old and a 6-month-old. Every once in a while, my wife will say, oh, I think our daughter's regressing. Like, she's a really good sleeper. She sleeps really well. She sleeps all night long. But then every once in a while, she wakes up in the middle of the night, you know, and cries a little bit. And then my wife will get worried. Oh, no, she's regressing. So have you heard that use of the word regressing? To regress? Okay, maybe yes, maybe no. Regressing kind of means like you're going backwards, right? You're no longer going towards your goal. You're regressing away from your goal. Okay, well, that's not at all what the word means in mathematics. I just wanted to check to see if we use the word regression in our normal everyday life. Anybody else? How we use the word regression? Okay, so in math, regression refers to a line of best fit. So here's Desmos. Desmos has a really cool regression tool. If you just Google regression calculator online, then Desmos has this tool already. And let's just say that these data points were data that we collected from our class. Like, for instance, maybe the data is, I have some data of everyone in the room's shoe size and height. So let's say that the x-axis represents shoe size and the y-axis represents height. Then would this data be believable? Do you believe that, generally speaking, as a person's shoe size gets bigger, their height also gets bigger? Yeah. So this is, this is a scatter plot, right? It's just a scatter plot representing data. Data is always messy. It never lines up exactly on a straight line. So the fact is, we could have somebody who's, okay, again, this is shoe size. So I could have someone with really big feet, but they're super short. So that, wait, I'm sorry. There we go. That'd be really, I don't want to ruin my, there we go. So this person has really big feet, but they're short. Whereas this person up here has really tiny feet, but they're somewhat tall. Anyway, what you'd really expect, though, is that in general, as a person's shoe size gets bigger, their height also gets bigger. And so here's the data. Now you've been watching. What's my line? What's my orange line doing? It's the line of best fit. So what we're saying is, if you just take some data of some people, you can calculate a line of best fit, which would then be your y equals mx plus b, which would be your best guess about how shoe size and height go together. So looking at this line, let's just say that this was the data that I had on shoe size versus height. And generally speaking, yes, as people's shoes get bigger, their height gets taller as well. Or you could say as they get taller, their shoes get bigger. So the line of best fit there, they went ahead and calculated it for us, is y equals mx plus b, where the m is 0.79, that's my slope, and my b is 1.6. Now, that's all well and good. So you draw a line of best fit, and then you can make predictions, right? You can say, well, what if I had somebody whose shoe size was an 8? Then you would use the line of best fit to predict how tall that person would be. Or vice versa. You could say, let's say I have somebody who is 5'7", you can predict what their shoe size would be. So that's why we use a line of best fit. You take a messy situation, like the fact that humans are humans, you know, it's not a perfect relationship between shoe size and height, and you make a line of best fit, which is just going to be your best prediction model for a shoe store. Okay? Now, there's one more piece of data on here. Not the m and not the b, the slope and the y-intercept, but the r squared value. Okay? This r squared value represents, the r squared value is always going to be between 0, well, between -1 and 1. And I should really show some data like this. Let me get some correlation coefficients here to show you. Correlation. Here we go. This is a good one. Darn, I wish I could make that bigger. That's okay. All right, well, that's okay. So, let's say that you have data that has no relationship at all. Like shoe size and height, that goes together fairly well. What if you related shoe size and eye color? There would really be no relationship there, right? So your data would just be completely messy. No relationship at all, therefore the r squared value is 0, meaning there's 0 relationship. As your data becomes tighter and tighter, like as we move over here to the left, this, generally speaking, the data is moving up. This, the data is definitely moving up. And here, you've got a perfect relationship between your input and your output variable. The r value goes between 0 and 1, where 1 is perfect. That means that data is perfect. Your prediction ability is perfect. Whereas an r squared value of 0.9 means your prediction ability is pretty good. The data, generally speaking, falls on the 1. An r squared value of 0.5, you can tell that it's positive, but the data is very sloppy. And so on. Then, so by the way, what is the positive 1 referring to?
Slope.
The slope. The fact that it's a positive slope. Now moving over here to the right, you have an r squared value where, well, no, I'm saying r squared. Maybe I'm actually intending r. Now you have a negative value, and the slope is negative. And as that value approaches 1, the data gets tighter and tighter and tighter into a perfect line. So we have this correlation coefficient that ranges between 1 and -1. 1 and -1 are perfect. The data is perfect. You can predict completely what your data is doing. That's very unlikely in real life. You're much more likely to have a value of, say, 0.9, where the data is fairly nice and clustered, and you can make fairly good predictions. And then 0 means you have no idea. Not that you have no idea, but there's probably no relationship, right? There's probably no real relationship in the data. Okay, so this is what we're talking about when we talk about regression and correlation. So this whole chapter here, 2.7, is talking about regression. The least squares regression, let's look at our notes here. The least squares regression, a statistical technique for fitting a line to data that minimizes the differences between the line and the data values. What that basically means is you do a regression to do a line of best fit. So the regression refers to the line of best fit. The correlation coefficient refers to that relationship between -1 and 1. Okay, and there we go. The coefficient of determination, r squared, is a measure of the goodness of fit. The closer it is to 1, the better off you are. Okay, so those are some general ideas. Let's go ahead and look at some data. So here's some data. The census data for Lake County, Ohio is. So, just looking at that data, can we say anything about Lake County, Ohio? Yeah, do we all agree the population's increasing? So let's just make a quick sketch. Quick sketch is very valuable. This is number 1. We're going to make what be our x-axis? Yeah, we're gonna put time on the x-axis, and we'll go ahead and just say, I'm gonna put 1970 right here. 1970, 80, 90, and 2000. And then on the y-axis, we're gonna put population. And the population ranges from 197,000, 212,000, 215,000, 227,000. So basically, we're just interested between 190,000, 200,000, 210,000, 220,000, and 230,000. Now you notice that I took some creative liberties with my graph. You know, I decided to start my graph there at 1970, and so that I'm somewhere on the x-axis, and I decided to start my population around 190, because all I'm really going to be interested in is the relationship of the dots to each other. So I don't have to take my y-axis scale all the way to 0. I don't have to take my time all the way to 0. But that's my data. So now let's try to put in some dots. In 1970, the population was 197,000. That's about there. And then in 1980, the population was 212,000. That's about there. Then in 1990, the population was 215,000. That's about there. And then in the year 2000, my population was 227,000, which is about there. So is it a perfect line? No. That'd be shocking if it were. So that just gives an idea, right? So we know for sure that our slope is positive, so we should expect an R value to be positive. And it's not bad. Like, just kind of draw a line that you feel like goes through it fairly well. Now you're just doing this by hand. There's no wrong answer, so long as you generally have a line going in the direction of your dots. If your dots look like that and you drew this line, that would be wrong. Right, you want your line to, generally speaking, follow the direction of the points. And I'm just going to ballpark a number here. I'm just going to say, hey, that looks like a 0.8. We're just saying that off the top of our head, the data is following a positive trajectory. It's fairly closely aligned. And all of that was just, we say spitballing? You ever heard that phrase? Spitballing? You're just kind of making an approximation. Okay, so now let's do the actual problem. To do the actual problem, folks, you would need to use your graphing calculator. Because it says, find the least squares regression line for these data and comment on the goodness of fit. Interpret the slope of the line of best fit. So everybody, take out your graphing calculator. I'm going to walk us through typing it all in. If you don't have a graphing calculator with you, please scoot next to a buddy who does. And you can follow along and watch. So, first things first, we need to go into, you see where it says y equals? Right above it, it says stat plot. At least I'm assuming that for most of you, it'll be right above that. Some calculators are slightly different. But if you go above y equals to stat plot, everyone hit second y equals. So option or second y equals. Now you're in a plot area. It says plot 1 off, plot 2 off, plot 3 off. What we'd like to do is go ahead and turn plot 1 on. So if you just hit enter, it takes you into plot 1, where now you can have your choice between on and off. And your cursor is blinking. So my cursor is already blinking on the word on. I'm going to hit enter again. Now my plot is on. Now, under type, you can tell that the very first one is already highlighted. It's just a scatter plot. It's a bunch of dots. The first one's not highlighted. Go ahead and highlight the first one, which is the scatter plot of all the dots. Next, you should notice that under X list and Y list, it should say L1 and L2. So make sure that it does say L1 and L2. If it does not say L1 and L2, please raise your hand right now. Okay, because I wouldn't necessarily want to. Oh, okay, so here, you're in Y equals, you have to put the second Y equals. Now you're there, and your plot's already on, and it is L1 and L2. All right. Yes? Yeah, yours is different. I have no idea. I would have to sit down and build a relationship with that calculator. It'd take me probably 30 minutes to figure it out. So, but look on your neighbors, okay? Okay, anybody else? All right. So, we're ready now to put in our data. All right, so now everybody, we're done with that screen. Hit second mode, that second quit. Just quit out of it. Now what we're going to do is we want to put some statistics into our calculator. So we're going to hit the stat button. Stat. And the first thing you see is it says edit. So go ahead and hit edit. And it should take you to a screen where you now have a bunch of columns that are headed with L1, L2, L3. Anybody know what L1 means? L2? A word that starts with L? Good guess. List. List 1, list 2, list 3. So under list 1, let's go ahead and put in our X values. So we're going to put in, just type in 1970, enter. 1980, enter. 1990, enter. 2000, enter. So far we've built a table of values with our X values, which are the years. Now if you hit to the right, the arrow button to the right, now you're in list 2. And you can go ahead and type in all of that data. Be very careful. 1972. And hit enter after every number. 2, 1, 2. Okay, anyone questions right now? Does everyone have all that into their calculator? Please let me know. Okay. This is about to get really exciting. So, if you're all ready with that, now, once again, you can hit second quit, go back to your normal calculator screen. Now what we're going to do is go into our window. The window, top left, well, it's, towards the top left window. If you go into your window option, oh, nope, sorry, not window. Gosh. What was that thing? Zoom. So sorry, zoom. Top middle, zoom. When you go to zoom, the option isn't right there. You have to scroll down, 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 down to option, well, it's my option 9. But it says zoom stat. Zoom stat. Do you all see zoom stat? Now if you hit enter, ooh la la. Do you see your graph? Pretty cool, pretty powerful, pretty neat. Yes, Lily? You got an error. It is a main mismatch. Let's see here. Y equals, there's your plot, and plot is on. All that looks right. There's your stats. Edit. You have an extra 0 there. Let's delete that. Yeah, no, that's okay. But you have to have the same number of X and Y coordinates. Now hit zoom stat again. Okay, so does everyone have their graph? So just looking at it, you can tell it kind of looks like the graph we made by hand. Yes, Josh? No. Okay. So now what we want is our line of best fit and all the data. Okay? One more button to push, everybody. Go back to stat. Now again, you have edit, calc, and tests. We now want to go to calc. We're going to calculate some statistics. And if you're on your screen there, it says 1 variable statistics, 2 variable statistics, mean, and then linreg, which stands for linear regression. So if you go down to my option 4, but just go to linreg, lin regression, you'll notice below that there's also quad regression, cubic regression, quartic regression. There's a lot of different types of regression you can do to not fit a line of best fit, but a parabola of best fit. Okay. Anyway, choose linreg, hit enter. It says linreg ax plus b, hit enter again. You have to enter twice. Well, yeah, mx plus b. Yeah, it says ax plus b, but it's mx plus b. Now, what do we have there? What that just gave us was just the line. And what they're saying is that if you have y equals ax plus b, which is really mx plus b, the values that they give us is the slope is 936.31 x, and then the y-intercept is negative 164.532. Okay, so that's what they just told us, that if now we graphed the line, that line right there, if we graphed it, it's going to go through those dots very well. So let's check it. Everybody now hit y equals. You should notice that your plot 1 is highlighted. That's just telling you that your plot 1 is already being plotted. But now under y1, go ahead and write that in under y1. Type in 936.31, and then x, you need the xt theta n button. So xt theta n, that's your x variable. So 936.31x minus that long 1, 6, 5, 2, 3, 6. Almost there. As soon as you have that typed in, you can hit graph. Graph. And now you're going to see something really exciting. Just keep that in there.
I just- oh,
Okay, and now hit graph. Hit graph, and what do you see? You see a line through the data. Oh, I tell you what, that wasn't the most exciting thing we did today, huh? You plotted some data and you drew a line through it. That was exciting. Okay, now there's the least squares regression line. That's it. This is the least squares regression line. Now it says comment on the goodness of fit. Pretty good. I don't know what else they want us to say there. It's pretty good. Interpret the slope of the line of best fit. The slope is positive because the population is growing. Okay, well that's kind of it. Now the one thing that they didn't give us right then, they did not give us the R squared value. It did? I didn't see mine. Well, mine didn't. What do you mean it did? It gave that to you on your screen when it calculated it? Oh, you did? Yeah, you guys did. What the heck? Why did mine not? You got an A, B, and an R. I only got an A and a B. Yeah, but yours is better. Your TI-82 did better than mine. I had a TI-83. Yours had it too. What is wrong with my calculator? I take this personally. Let me try again.
Haven't spent enough time with it.
Jeez. Okay, well, I didn't get the R squared value. Please, Chelsea, tell me the R squared value.
Well, so it says R.
Yeah, R.
0.96961845.
Okay, perfect. So the R value is 0.969. That's pretty good. That's really close to 1. Remember, your R value is anywhere between 1 and -1. That's a positive 0.969. That's a very good fit. Okay? Okay, so now it says use the regression line to predict the population in 2010. Okay? So how does this work? If I want to know the population in 2010, then what is 2010? That's my X value. That's my input. I just take 2010, plug it right into the formula. This is great. This formula now, the linear regression formula, is going to predict for us what the population will be in the year 2010. So we'll go ahead and plug in 936.31 times 2010 and subtract away just on your normal calculator screen. So go second quit, normal calculator screen, and do 936.31 times 2010 minus 1. I got, in the year 2010, population is 236,650.5. I guess someone is pregnant. Or someone is short. I don't know. Could be a baby. No, it's just a decimal, right? So that's the population. That's the prediction. How was that prediction according to the census? The actual value from the census was 230,000. So that was the prediction. This was the actual 230,000. How is the prediction compared to the actual?
It's a little bit above 960.
Yeah, I mean, it's close. It was in the 230,000s. Is it close enough? Well, that depends. You predicted 6,000 more people than you had. So what does that mean? You put more money into police officers, firefighters, infrastructure, water, everything that your city needs, than you actually had people to use it, right? So if you were preparing to have 6,000 more people than you did, you probably did a lot of preparation that was unnecessary, right? Those would be decisions that city managers and mayors and townspeople would have to make, right? Like, oh, geez, we think our town is going to have 236,000 people by the next 10 years. We better be ready for that and build bigger roads and et cetera. And then 2010 rolls around and they're like, oh, we didn't have as many people as we thought. Right? So city planning wise, this would be very helpful to have good, accurate prediction of the future. Okay, how does everyone feel about that? So what's the next question? Use the regression line to predict when the population will reach 250,000. So everybody, for a moment, let's remember, what we have here is a function. The regression line that we just found, f of x equals 936.31x minus 1,645,332. This thing's a function, right? And so what can you do with functions? You got two options. You can plug something in or set it equal to. So this question is saying use the regression line to predict when the population will reach 250,000. So remember, what is our input? The year. What is our output? Well, what is this output? The population. So where do we put, if they're asking when will the population be Population. Where would we put the 250,000? Would I plug it in, or would I set it equal to? You'd set it equal to. So now you take that whole nice long equation, 936.31x minus 1645332.16, and you set it equal to 250,000. Now see again, for a city planner, a governor, people on the city government, people on the, whatever it is, and whoever these people are who help to run a city, whose responsibility is to think about the city, this is the kind of prediction model that they would need. So we're going to add that number over. I'm going to do this all in my calculator. I know I'm going to add the 160-something number over. Then I'm going to divide by 936. So I'm going to take my 250,000. I'm going to add the 1645332.6, and then I'll divide by 936.31, and I get. I did something wrong. 1645. Oh, I did do something wrong. Okay, that's good. I got the year 1783. Did I do something wrong if I got the year 1783? Probably. So now, 936. I got the year 2024. So when will the city reach a population of 250,000? In the year 2024. So again, for city planners, they would want to know that so that they can say, okay, well, we've got, what year is it, 2019? We've got 5 years. 5 years to do whatever infrastructure and building that we need to prepare for this larger population. Okay, was that fun? Is that interesting? I would say it's particularly interesting because what information did we have? Just 4 pieces of data. Right? Just 4 pieces of data about what the population was in the past. And from that 4 pieces of data, we're able to come up with an actually really good model that will allow us to predict the future population and what year it will be. And that will allow for some really good city planning. Provided that actually keeps happening. That the population really does continue to grow. Okay, well, we've got 2 more problems like that. By the way, how does this feel compared to everything we were doing earlier today? What, Jackie? No? Is this very different? This feels very different. Are we doing any heavy-hitting algebra? Or solving quadratics and factoring? No, this is a very different type of activity. Well, I guess I don't have to erase that. All right, folks, the next problem, number 2, looks identical. Let's not do number 2. That's Lorain County. So let's do number 3. Using the energy production data given below. So what does this mean? Production in quads. So this is 1950, 60, 70, 80, 90 to 2000. And they're producing energy, apparently. And those numbers represent quads of energy. Anybody have any idea what that is? See, this is the fun part about reading a word problem in a math class. Sometimes the word problems, you're like, what? What's a quad? Anybody ever heard of a quad unit of energy? Let's just take a look here. Energy production quads. Whoop, it looks like it could actually mean something. Electricity generation is down by 2.8 quads. Oh no. Anyone know what a quad is yet? Oh, here we go, Wikipedia. Trustworthy source. A quad is a unit of energy equal to 10 to the 15th short scale quadrillion BTUs, or that many joules. The unit is used by the Department of Energy in discussing world and national energy budgets. The global primary energy production in 2004 was 446 quads. Geez, that's the whole Earth. So in the year 2004, all the people everywhere produced 446 quads of energy. So some common types of energy carrier approximately equal to 1 quad. Okay, so here we go. 100,000, million, billion. 8 billion gallons of gasoline is 1 quad of energy. So the last time you put gas in your car, did you put 8 billion gallons? Probably not. How many gallons do you put in your car? 15, 10, 15, or 20? So considerably less than a quad. So anyway, there. Now we have it in perspective, right? A quad is 8 billion gallons of gas, and the entire world produced 446 quads of energy in the year 2004. So let's go back to our problem now. This was the energy production data given below. So let's keep in mind that for the whole world, the energy production in 2004 was 450-ish, and this is 71. Who do you think this represents? If the whole world in the year 2004 was 446 quads, and this is 71 quads, who are we talking about? Maybe just the United States, to be honest. I mean, you might say like North America, US, Canada, Mexico. But could it just be us? It could actually just be us. We produce a lot of energy. We do a lot of consumption. So this data could be representing the US. Do we know? We have no idea. This could be completely made up data about nobody. But at least now we have some sort of perspective that this could just be talking about the United States and how much energy we're producing in the US. So generally speaking, how much energy we're producing? More and more and more, right? So now we know what we're talking about. Plot the data using a graphic calculator and explain why it does not appear to be linear. Oh, well, that was fun. Everyone back to your calculators. We'll start the process over, okay? Because that was a lot of steps that I did with you. We're going to finish this problem. So step one, you can hit clear, 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 and clear out your main calculator screen there. Let's go back to stat. We want to go into edit. So stat and then edit, and we want to change the data now in our L1 and our L2. So if you use your cursor to go back over to L1, I would believe what you're going to need to do is hit clear and then type in your new years. So you're going to hit 1950, enter, then clear. 1960, enter. Oh, actually, you can just start typing. So 1970, it automatically rewrites it for you. 1980, enter. 1990, enter. 2000, enter. So you can just overwrite L1 with all your new years. Now hit to the right. Now you're in L2, go all the way up to the top. And now start typing in your quads. Quads. Oh yeah, quads, of course, because these are your quads, right? Okay. So 35.6, enter. 42.8, enter. Okay. So you now have your new data. Now what do we have to do? If we just go graph it right now, our window is not correct. We're in the wrong area. So what do we need to do? Zoom. Once you have your data in, now hit zoom and go back to zoom stat. Zoom stat. And that way it's going to zoom you in right on your data. Now keep in mind, if you're like me, you still have that other line being graphed right now. So you might want to go back into y equals and clear out that line that you had, the 936 line. So now that's cleared. Go back to graph, and there's our data. So first of all, what does our data look like? If your data is like my data, which it should be, it goes over and then like that. Is that what it looks like? Yeah. So is that linear? Not really. It looks like there was a huge spike from 1960 to 1970. Something happened between 1960 and 1970 where we were able to start producing a lot more energy, and or the demand was much higher, so we simply started producing more energy. I don't know. Do you think that could have corresponded with nuclear energy or building more nuclear power plants? I don't know. Could it also have had to do with the EPA having regulations about cleaner energy? I don't know. We don't know anything, right? We're just looking at data. So now what? It said plot the data, explain why it doesn't appear to be linear. Well, there were a lot of new technologies in the latter half of the 1900s. So you've got new technologies, you've got growing population. Population isn't necessarily linear. Normally population is exponential, the way people grow and give birth to babies. So there's a lot of different reasons why it might not be linear. It could have to do with, like I said, EPA policies about energy. It could have to do with nuclear energy. When did people start producing nuclear power plants? Was it around that time? Early 60s? Okay. Okay, part B, discuss with your classmates why ignoring the first two data points may be justified from a historical perspective. Not a bad idea. See, if we put a line of best fit through it now, our line of best fit is going to be terrible. Whereas if we ignore the first two data points, then our line of best fit would be awesome. So why would we be justified in ignoring the 1950s and the 1960s? Right, it is different. And why is it different? What do we have now that they didn't have? Yeah, all sorts of new technology, right? So who cares about the 1950s and the 1960s? Right now we have different technology, so we should only be focusing here. If we want a good model that will predict the future, we should stick with just using these data points and ignore those data points. Find the least squares regression line. So everybody, just to remind you, how do you do that? Well, first of all, we probably want to delete those first 2 points. Right, so how do we delete those first 2 points? We have to go to stat, we have to go to edit, and then we have to go over to the 1950, and I think you have to hit delete. And then delete again, and then go over to L2 and hit delete and delete again. So now I just have the good data, and now we can go into stat, calc, and go down to lin regression. And when you hit enter, everybody should have y equals 0.266x minus 459.86. So you can confirm your answer. And then you would do the next 2 activities. Use the regression line to predict the energy in the year 2010, and then use the regression to predict when will the energy production be 100 watts. So it's just like the previous example. Okay, now, I know class is almost over. So what do you all need to do? Well, first of all, I think about half of you still need to come see me in office hours, because in my syllabus it states come see me in office hours before the day of the first test, and the day of the first test is, I believe, next week on Monday. So I suggest if you haven't been to my office yet, you come with me right now. Just come up with me right now. It'll take all of a minute of your time, right? Otherwise, you need to come into my office tomorrow. I'm in my office for a short period of time between 1 and 2. And then otherwise, you'd have to come in Monday, like first day. So I say do it now. Your test is on Monday, February 11th. What do you need to bring with you? Your practice test completely filled out. And P.S., you have no reason not to fill out the practice test because I posted the solutions on Canvas. Right, so at the very least, you can use that as a guide to help you fill out your practice test. Also bring with you your chapter 1 and chapter 2 notes. You do not need to turn in all the practice we did on Monday. All that factoring practice, that was just bonus little packets I passed out to you so that you could practice. So you just need to turn in your chapter 1 notes, your chapter 2 notes, and your practice test. That's what's due on Monday, and you're taking your test. Okay? That's it. If you have any questions, come see me. I'm going up to my office right now.
I have a question.
Yes.
About the graphic calculator.
Yes.
Were you making them out, or were like the big story?
Oh, you know what? I would have to go ask in the math department. The person at the front desk, her name is Karina. She could tell you. I will bring some extra graphing calculators with me to class on Monday. So if you don't have a graphing calculator yet, I'll have one for you to borrow.
Hey, you might know since they're on the.
Yes, yes, definitely, Abe. You can do that.